Okay. So okay, so this is Alexandrov's theorem, and we'll try to prove this. We will prove this. So I just wanted to say that we don't have many classes left, right? I think till May 19th is our last date. So uh, I think next Tuesday is a holiday, is it correct, for Eid?
Yes, sir.
Yes, sir.
Right. So,
Yes.
okay, so we have this class, and then let me just check the calendar. So, third is a holiday. So then we have the 5th. So we have 5th, that's one class. And then 10th and 12th. So 1, 2, 3. And then 17th and 19th, 4, 5. So we have 5 classes left. Okay. So we'll prove this theorem by the end of that. And then in the remaining time, I'll maybe try and tell you a bit about, I guess, maybe the geodesic flow and negative curvature and ergodicity and Mostow rigidity and the Mach length spectrum. I mean, those are all big topics. We don't have time to cover them properly, but I can give you some sketches of proofs, if that's okay. So would that be all right as a plan?
Yeah, that would be great.
Yeah, I can just give you some sketches of ideas of the proofs. We won't have time to do them in detail, all right? But I can give you the ideas of the proofs. I can give you ideas of the proofs. This theorem will be more or less the last thing we'll do in detail, is Alexandrov's theorem. We have time enough to do this in full detail. So we'll do this theorem, all right? And after that, what time remains, I'll just do sketches of proofs and give you some ideas, all right? So that's the plan for the next 5 lectures. And maybe we'll spend one lecture on problems. I have to think of some problems. I'll try and send you some problems next week. And then, I mean, the exam, there'll be a final exam. It will be just from the problems that we do in class, okay? And those will be also quite simple problems. So don't worry about the exam, all right? Okay. Yeah, I mean, presentations would have been good, but I mean, I can't really give you material to present. We've more or less covered everything. So, and it's not a reading course as such. So it doesn't make sense to ask you to present really. So we'll have just a regular exam. It's you just, you can just email me your answer scripts. I'll send you. Okay. So we can have it on the week after the 19th. Is that all right? For the exam? Yeah, so maybe on the 24th, if we have the exam, is that okay? Yes?
Yes, sir.
Or 26th if you want some more time. Whatever.
Okay.
Yeah, so either 24th or 26th. You let me know what you prefer. I would prefer 24th because then I can finish grading and give you back in the same week. I mean, it won't be anything difficult. Okay, the exam, it'll just be things we've done in class. So, okay, so just things we've done in class. Okay, so let's now start working towards the proof of Alexandrov's theorem. Okay, so for that, we'll need to understand. So we talked about H2 in previous lectures, the hyperbolic plane, right? So we'll need to talk about Hn. So before that, let me just do one lemma, which we've more or less done before, but okay, I'm just stating it maybe in a slightly different way. So let M be a complete Riemannian manifold. and let theta equal to x comma u be a unit tangent vector in T1n. So x is a point of n and u is a point in T1xn, a unit tangent vector at x. And let xi be an element of T theta Tm, okay, such that j theta of xi is 0 comma v, where v is in Txn with inner product uv equal to 0. So remember, what is j theta xi? This is d pi theta xi and k theta xi, right? So this is the horizontal and the vertical component of xi, right? Okay, so the horizontal component is 0. D pi theta is 0. And the vertical component is v, okay? And let gamma be the unique geodesic with initial condition theta, and let j xi be the unique Jacobi field with initial conditions j theta xi. So that means that j0 is 0 and j prime 0 is v, right? So this is the sort of Jacobi field you get by taking a one parameter group family of geodesics passing through the point x in this case, right? So here is this is x, this is u, okay, and then I'm taking basically this is I'm taking a perpendicular vector v, and then I'm taking my Jacobi field is like this, right? Is this clear? Yes. So I have my Jacobi field, j0 is 0 and j prime 0 is v. Okay, so this j I can write as jt is del del s at s equal to 0. Or if I take the geodesics with initial condition u plus sv, right? Is this clear? This will give me a Jacobi field like this. Is this clear? Yes, we've seen this construction before, right?
Yes. Yes.
Yes.
Yes, okay. These are geodesics passing through the same point, x, right? Like basically rotating the geodesic around x, okay? So that gives you a Jacobi field with j0 is 0 and j prime 0 is v. V is perpendicular here, so. So then we've already seen, that such a geodesic, such a Jacobi field is a perpendicular Jacobi field, right?
Yes, sir.
We've seen that J belongs to J naught of gamma, i inner product JT gamma prime t is 0 for all t. Okay. So that's one part. So now what I can do is I can define for any t, I can define a map from so let me call this j equal to j sub v, okay, right? So this is this depends on v, right? The initial conditions are 0 and v, okay? So I can define a map, let me call it for any, I fix a t, fix a t naught positive or non-zero, and define a map phi from the orthogonal complement of u. So this is in Txm to the orthogonal complement of gamma prime T naught. So this is in T gamma T naught M. Okay, so in this picture, this is gamma prime T naught. And this is the orthogonal complement, right? So my J takes values here, right? In the orthogonal complement, because Jt gamma prime T is 0 for all T. So I can define this map V goes to Jv of T naught, right? This is a linear map because Jv depends linearly on V, because the initial conditions of J is a linear function of V, right? Yes?
Yes, sir.
Okay, this is a linear map. Okay, from the orthogonal complement at the origin to the orthogonal complement at time T naught. So then what can you say about this map? What kind of linear map is it? Oh, suppose the sectional curvatures are non-positive. Suppose K P sigma less than or equal to 0 for all. Oh God, this is getting stuck. Sorry. P and N sigma then what can I say about phi? What kind of linear map is it? Yes, anyone? Anyone? Yes, are you there? Hello?
Yes,
Are you
sir.
there?
Trying to
Yes.
think.
So yeah, I'm giving you that the sectional curvatures are non-positive, right? So then what do you know about Jacobi fields in non-positive curvature? What did we prove when we did the Cartan-Hadamard theorem?
Will stretching sometimes?
What did we prove about the norm squared of Jacobi fields? As a function of t, what kind of function is it? Remember, we used the Jacobi equation to prove something about Jacobi fields in non-positive curvature. What did we prove? You don't remember? Anyone? Yes.
The norm of the Jacobi fields remain constant.
No, not at all. Not at all. Not at all. Come on. We talked about Jacobi fields in H2. They grow exponentially. They decay exponentially. They're not constant. Not at all. What are you talking about?
Norm remains norm, I mean, positive.
Huh? What? Yes.
Does it mean that JBT will not vanish at all?
Right. Exactly. Exactly. If V is non-zero, then JVT is non-zero, right? So then phi is 1 to 1. Its kernel is 0, right? Why is this? Because the norm squared of Jacobi fields is what kind of function is it? What kind of function is norm squared of the Jacobi field in non-positive curvature?
Convex.
It's a nice. Yes, exactly. It's a convex function, right? So if it's a convex function which is non-negative, then if it vanishes at 2 points, then it vanishes in the whole interval in between those 2 points. Yes?
Yes.
So that means
Yes.
the norm squared becomes 0 on an interval. That means the Jacobi field is 0 in an interval. That means in that interval, J and J prime are identically 0. Yes? Yes? But then if J and J prime are 0 at 1 point, then the Jacobi field is identically 0, right? Because it's a solution of a second order linear differential equation. So if the initial conditions at 1 point are 0, then the solution is identically 0, right? Right. So therefore, in non-positive curvature, a Jacobi field can vanish at most once, right? So here we're already given that J0 is 0. So if JVT0 is 0, then J has to be identically 0. So therefore, J prime 0 is also 0. So then V is 0. So that means the kernel of this linear map is 0. So phi is 1 to 1, hence is an isomorphism, right? Is this clear?
Yes.
Yes.
Okay, this is an isomorphism. In fact, I mean, you can also write this in terms of the exponential map, right? This will be if I just use the chain rule, what is this? It's this is TU plus TSV, right? So actually, what is this? This will be dx x at the point TU, T naught U, right? Applied to the vector T naught V. Is this clear? Yes?
Yes.
Yes.
And in the proof of the Cartan-Hadamard theorem, what did we show? We essentially showed that the exponential map, we showed it's a local diffeomorphism, right? So its derivative is everywhere invertible, right? Its derivative is an isomorphism everywhere. Yes?
Yes.
So that will also tell you that this map is an isomorphism, right? Because it's just the derivative of the exponential map at the point T naught U, right? So that's an isomorphism. Is it clear? Yes?
Yes.
Yes. Sir. Yes.
All right. So what does that mean? That means basically given any vector at time T naught, right? I can find a Jacobi field whose value at time T naught is equal to that vector, right? Any perpendicular vector at time T naught, I can find a Jacobi field whose value is equal to that perpendicular vector. All right? Okay, so all right. So that is this this lemma that I've written here. This is an isomorphism if K is less than or equal to 0. Okay, so we know this. All right. Now I want to come in the remaining time, next 15 minutes, quickly go through the n-dimensional hyperbolic space. Okay, so this is the higher dimensional analog of H2. So this is going to be called Hn. So for n greater than or equal to 2, let ds squared be the Euclidean metric on Rn. So the n-dimensional hyperbolic space, like the two-dimensional hyperbolic plane, there is an upper half space model, and there is also a unit ball model. Okay, so let's talk about the upper half space model first. So as a Riemannian manifold, it is the upper half space in Rn, that is points of the form x bar comma xn, where the last coordinate xn is positive. Okay. And the metric is just like in H2. It's the Euclidean metric ds squared divided by the last coordinate, the height squared, xn squared. Okay. This is the Hn, the upper half space model of n-dimensional hyperbolic space. So just like in H2, you can see that translations, horizontal translations, are isometries, right? If I take a translation x bar comma xn goes to x bar plus v comma xn, right? So then this preserves the Euclidean metric and it preserves the height. Therefore, this is an isometry, right? Yes?
Yes.
And similarly, scalings are also isometries. So x bar comma xn goes to lambda x bar comma lambda xn, where lambda is positive. Yes, because this scales the Euclidean metric by a factor lambda squared, and the height squared gets also scaled by lambda squared. So therefore the ratio stays constant. Is this clear?
Yes.
Yeah. Okay. And also we, in higher dimensions, we have a new kind of isometry now, where I do a rotation in just the x bar coordinate in the first n-1 coordinates. So x bar xn goes to O x bar comma xn, where O is in SO n-1. All right. Is this clear?
Yes, sir.
So this tells me already that the group of isometries of Hn, it acts transitively on Hn, right? Because given any point x bar comma xn, by a horizontal translation, I can move it to a point on the vertical xn axis, 0 comma xn. And then by a scaling by 1 over xn, I can move it to the point 0 comma 1. All right. So every point I can move to the point 0 comma 1. All right. Is this clear? Just by translations and scalings. Yes?
Yes.
So for Utshab, this is the N group and this is the A group, right? These translations are the N group and these scalings are the A group. All right. This is your NA group acting transitively on itself.
Yes, sir.
Okay. All right. So Hn, the isometry group, acts transitively. Okay. Now, I want to come to the ball model of the unit ball model. So for that, I need a map like the Cayley transform. So for that, we're going to, so that the Cayley transform in 2 dimension is a Mobius map. So Mobius maps are generated by inversions in circles and reflections in lines. So in higher dimension, we also have Mobius maps. Those are generated by reflections in hyperplanes and inversions in spheres. So what is the inversion in the unit sphere? It is the map x goes to x over norm x squared. Okay. So what is this map doing? So okay. So Hn. So we have the upper half space model. That's Rn minus 1 cross 0 infinity ds squared over xn squared. Okay. Now, what is inversion in the unit sphere? Basically, I take the unit sphere in Rn. This is Sn minus 1. I take the origin. I take any point x which is non-zero. Then I look at the ray passing through the origin and going through x. I extend this until I come to a point x star. This will be the reflected point under the inversion, such that the product of the distances norm x into norm x star is equal to 1. Okay, so that you can see it implies that x star has to be x over norm x squared, right? Is this clear?
Yes.
Okay.
Yes.
Now what I want to do is look at what this does to the Euclidean metric. Okay, so what does this inversion do to the Euclidean metric? So for that, notice that basically if I take a sphere of radius r, this will map to a sphere of radius 1 over r. Yes? Yes, that's clear from the definition, right? Yes?
Yes.
A sphere around the origin, And also straight lines through the origin map to themselves, right? So this straight line through the origin will map to itself, okay? So here's x, and here is x star. Okay. Now, since it maps the sphere to the sphere, the tangent space to the sphere here goes to the tangent space to the sphere here, right? Under the derivative. Is that clear? Yes. And also this straight line through the origin goes to this straight line through the origin. So this tangent, this perpendicular normal vector to the sphere goes to this normal vector to the sphere in the opposite direction. Yes, is this clear? Yeah. So if I look at the derivative of this map at x, yes, then it sends basically, so this is Rx, right? This goes to Rx. This is Rx. So, okay, well, okay. Let me write this below. So what does it do at the tangent level? The derivative maps. So I decompose the tangent space of Rn. So this is Rn, of course, but I decompose it as Rx direct sum Rx perp, which is the same as Rx direct sum the tangent space at x to the sphere passing through x. So the sphere around the origin of radius norm x, right? Yes? Okay. This maps under the derivative. So this is an orthogonal direct sum. This maps to Rx, orthogonal direct sum, tangent space at the point x star or Ix. of the sphere of radius 1 over norm x, right? Is this clear? Yes? Okay, which is again Rx direct sum Rx perp, right? Is this clear? Yes. So it preserves this direct sum decomposition because it maps straight lines through origin to straight lines through the origin, and it maps spheres to spheres, right? So therefore it maps the tangent spaces to the tangent spaces, and those give you a direct sum decomposition, right? Is this clear? An orthogonal direct sum decomposition. Yes. So
Yes.
in order to understand the what it does to the Euclidean metric, we just need to compute the derivative along this direction, along the normal direction to the sphere, and along the direction tangent to the sphere. Okay. So that's what we're going to do. And the claim is that the pullback of the Euclidean metric under I, so I star of ds squared, is norm ds squared over norm x to the 4. Okay. So this is what it does. So all right. So given an x naught with norm x naught equal to r, let's look at the unit tangent vector in the direction of x naught. That's x naught divided by norm x naught. Okay. And then let v be the orthogonal complement of v naught. That's the tangent space to the sphere of radius r. And now I look at a curve in the direction of the straight line through x naught, tx naught. And so dix naught of v naught will be basically ddt of I of gamma t, right? Divided by norm x naught, because v naught is x naught divided by norm x naught. So it will be 1 over norm x naught into ddt of I of gamma t will be what? It will be tx naught divided by t squared norm x naught squared, right? So when I take ddt at t equal to 0, at t equal to 1, not 0. This is a typo. This is at t equal to 1. Then I'll get x naught over norm x naught squared, a norm of that. So that's 1 over norm x naught, and then another 1 over norm x naught. So this is 1 over norm x naught squared. All right. Yes. Is this okay? So
Yes.
in this direction, lengths are getting in the normal direction. In this normal direction, lengths are getting multiplied by 1 over norm x naught squared. Okay. And what about in the tangent direction to the sphere? So in the tangent direction to the sphere, I take a vector which is in tangent to the sphere w naught, and I can choose a curve gamma in the sphere so that gamma naught of x naught is 0, gamma of 0 is x naught, and gamma prime 0 is w naught, right? And so then I look at dix naught of w naught. This will be the ddt at t equal to 0 of gamma t of I of gamma t, and I of gamma t is gamma t divided by norm gamma t squared. Norm gamma t squared is r squared. So this becomes gamma t over r squared. So this becomes gamma prime 0 over r squared. So this is norm w naught, that's 1 over r squared. So this becomes 1 over r squared. So this is 1 over norm x naught squared. So that means in the normal direction, it multiplies lengths by 1 over r squared. In the perpendicular direction, it multiplies lengths by 1 over r squared, right? Therefore, in the perpendicular, in the tangent direction to the sphere, it is basically 1 over r squared times an orthogonal transformation, right? If all lengths are multiplied by 1 over r squared, then it's just 1 over r squared times an orthogonal transformation from the tangent space to the sphere to the tangent space to the sphere, right? Yes. And in this direction, it's 1 over r squared times 1 well, minus identity in this direction. So using Pythagoras theorem, you get that the norm of di x naught of v, norm squared, will be the norm squared of v divided by x naught to the power 4. Is this clear? Yes. I mean, all I'm doing is basically, if I take a v, I write v as some whatever lambda x plus w, where w is perpendicular to x. Okay, so dix of v is dix of lambda x plus dix of w. So these are perpendicular to each other. So by Pythagoras theorem, or by just expanding out the inner product, this norm squared is equal to the sum of norm squares. Yes? Right?
Yes, sir.
And these, the norms are multiplied by 1 over norm x squared. So this will be basically norm of lambda x squared divided by norm x to the power 4. And this will be norm of w squared divided by norm x to the 4, right? So when I add these up, I'll get on top norm v squared and below norm x to the 4. Is this all right?
Yes, sir.
Okay, fine. Okay, so that proves it. So the pullback of the Euclidean metric is the Euclidean metric divided by norm x to the 4. Fine. So now I can give an isometry from the upper half space to the ball with the metric 4 ds squared over 1 minus norm x squared whole squared. So this is the unit ball model of the hyperbolic n space. This is just like the hyperbolic metric on the unit disk, right? So there's less than a minute. Let me stop and just do 5 minutes to tell you how to get this isometry. So let's just stop and start just a very short meeting, okay?